So in this problem, we have a bike going on a level road. So it makes most sense to call the level road y equals 0. The bike is moving and it comes to a stop. So it has an initial velocity, and yours will be different, but let's just say mine's 10 meters per second, and it comes to a complete stop. So you know the final velocity is 0. And because it's a level road, and we chose to call the road y equals 0, you know the height initial is 0, and you know the height final is 0. And of course, the work is not 0 because energy is not conserved. We had to take energy out of the bike and put it into the brakes in order to get this car to stop. And we do know the time, so that's going to be given to you in some form. And we are trying to find eventually the power. So this problem is actually going to involve two steps. The first step is going to be apply the work energy theorem. So I'm going to apply mechanical energy at the end, which is when the bike is stopped, must equal the mechanical energy at the beginning plus the work. You could write this all out, but since there's no kinetic energy at the end, there's no potential energy, the final energy is just 0. I guess I should do it. It's 1/2 mv final squared plus mgh final equals 1/2 mv initial squared plus mgh initial plus w. But of course, h final and h initial are both 0, and the final velocity is 0. And so this equation that's left, we want to solve for w, find out how much work is done. So you're just going to have 0 equals 1/2 mv initial squared plus w. And you're going to solve that for w, and I'll leave that up to you to do. Once you know w, the second step is going to be to use the fact that power equals w, the work, divided by time. And you're going to do that to find the power. Because the question was, what is the power of the braking system that is needed? So that's going to be how you solve that problem.